Okay, so number three. Three is a little bit complicated for this class. I mean, well, it's not complicated for this class. It just uses a lot of reasoning. But the reason why I want to do this is because it explains why when you charge up a amber rod or something, you can lift little pieces of paper. Or in this case, the way I'm going to do it, I think this is a bar electric. It doesn't really matter. It explains why these things why anything actually does that. So you remember, in the presence of the electric field, we end up with a polarized object. Now I'm going to talk about an electret, and an electret, like a magnet, always has a polarization, and that's going to let us skip a couple of steps, right? So we don't have to worry about, okay, the how much polarization is induced by this field, and as this thing gets closer to, as this cylinder gets closer to this guy here, it gets heavier and heavier. So we don't have to worry about all that. All we have to worry about are the things that we're going to do. So what we're going to have to do is we're going to have to find the force that'll be pushing this thing, pulling this thing up, because if this field is going that way, right, that means these are positive. Actually, it's pushing it down. I'm sorry. And so we have to figure out what that force is in this case. Um, but we know what its polarization is already. So we'll have to just make the approximation here that we've got a plus charge and a minus charge some distance away from each other. That's going to be 10 centimeters. All right. And this distance here between the center of the rod and this guy is going to be 25 centimeters. So that should be sufficient to get us going. And this is 1.11 microcoulombs per meter, because that's 100 divided by 9. Okay, so we'll have to find the field at each cap, and then multiply that by the charge on each cap to find the force. And we're going to have to add the two things together. So we're going to have to take the force here, or the field here, the force there. So we're going to have a force here coming down, F1, and we'll have a force coming up here, F2. We're going to add them together to figure out what the actual force is. Okay, let's see. Which way should I do this? Let's go for the field on each cap first, all right, because that's sort of the point of this episode. That is going to be Ke times lambda over this distance r minus that distance, which is going to be L over 2, right? The length of this thing is 10 centimeters. This distance is from the center of this to the center of that is 25 centimeters. So we have 25 centimeters, or r minus lambda over 2, L over 2. Okay, so now I'll go ahead and put things in. 10 to the ninth. Newtons meters squared per coulomb squared. The lambda is this guy here. 100, I said, over 9 millicoulombs per meter. So that's 10 to the minus 3. 10 to the minus 3 coulombs per meter. And I'm not going to have enough room to do all this. And then what else do I have? I have 1 over 0.25 centimeters minus 0.05 centimeters. Because it's right here, it's 5 centimeters less. That's 20, or meters, excuse me. I put the points in. Sorry. Not good, not good. Okay, 9s cancel. Sometimes it looks like I planned these things. So then we have 100 over 20 times 10 to the 9th times 10 to the 7th, or minus 7th. This is times 10 to the 1, 2 squared. Get rid of one of those meters there. And the other one here, right, those guys get rid of another meter. We don't have any meters. We get rid of that coulomb, so we have newtons per coulomb, which is good because that's units of field. Get rid of one of those. It becomes 5 times oh, this is too far off, isn't it? 10 to the... Oh, this is 3. Okay. So that's better. Okay. So 10 to the 11th minus 3 is times 10 to the 8th newtons per coulomb. And that's right. And here I do the same thing. So even though I'm going to stop because I didn't have enough room, this took me the entire screen. So instead of being 1 over 20 centimeters, this is going to be 1 over 30 centimeters. So instead of dividing by 2 here, we'll divide by 3. And so instead of 500, we get 333. Or instead of 5, we get 3.33. Right? So that's the only difference. You do the same thing twice. I know you love math. I know you want to watch me do as much math as possible, but there's no need to do it twice. You just do it the same way. All right, then we have charge on each cap. Now we'll find that with our definition of the dipole moment. D equals QL. Let's see, do we have what? So we want the dipole moment of this thing, which is 5 times 10 to the 6th coulombs per meter is equal to the charge on one of the caps. So this is Q, this is minus Q, times the distance, which is 0.1 meters. It's 10 centimeters difference right here. So that means Q for one of these guys has got to be 10 to the minus 6. Q has got to be, Q is 5 times 10 to the minus 5th coulombs. All right. And that's going to be positive for this guy and negative for this guy. Positive here and negative there. It's 50 microcoulombs on each side. Don't need that. Don't need that. Get rid of it. All right. And then we go to the force. The force is just going to be adding the two forces. So we have QE. This guy is getting pushed downward. This guy is getting pulled upward, right? QE, QE. And that ends up giving us 50 microcoulombs. That Q is the same for each one, excuse me. 50 microcoulombs times 500, or minus 500 times minus 333, minus 500 plus 333 times 10 to the 6th newtons per coulomb. That doesn't make me happy. Now 333 minus 500 is, what, 167. So we're going to do 167 times 50. That should end up being about 8.35. This is microcoulomb, so this is minus 6. Minus 6 and And 6 is cancel out, so we have 8.35 times 10 to the cubed kilonewtons. Okay. So that's minus 8.35. That should be a minus 8.35 kilonewtons. Okay, so the procedure there is calculate the field, calculate the charge on each cap, right? These have to be the same. This is always Q, this Q, positive Q at the tip of the arrow, minus Q at the bottom side. And then we multiply Q and minus Q by the two guys here. This is basically based on the signs here, based on the direction of this, the field. So if this is coming out, this is positive. This is the positive part, so it's going it's going to get pushed along the field, so in the negative direction. This guy, negative part, gets pulled in the opposite direction of the field, so it's positive, it's going up. Add those two forces together, and you get the force on this guy. So that is it for this one. Thank you very much. I will now get to the potential. Bye now.